In this video, we want to gain an understanding of inverse trigonometric functions. To understand inverse trigonometric functions, we first have to think about what is required for a function to have an inverse. And so, if we remember, a function f of x has an inverse function f inverse of x if for each output there is exactly one input. What this means in particular is that if there are two values, say f of 1 that is equal to say 7 and f of 2 is equal to 7, then if I were to try to define the inverse, f inverse of 7, I wouldn't be able to tell whether that was equal to 1 or if it was equal to 2. And since there's no way to tell those apart, you can't define that inverse because that inverse wouldn't be a function. So you can't have that type of a situation. Now, we've seen functions where this occurs. If we look at a function like f of x is equal to x squared, then if I look at 4 as an output, I can get that f of negative 2 is equal to 4 and f of 2 is equal to 4. So I can't have an inverse function. However, if I restrict my domain so if I restrict the domain of f to 0 to infinity, now, because I've restricted the domain to 0 to infinity, I'm no longer looking at anything with a negative number. And I get that f inverse of x is just equal to the square root of x. And so restricting the domain can at times fix this kind of reason for not being able to have an inverse function. With trigonometric functions, this will be a key to understanding the inverse functions. So first, we are going to look at the sine of x. And if I look at the sine of x, then at negative pi, my sine of x is 0. At negative pi over 2, my sine of x is negative 1. At 0, my sine of x is 0. At pi over 2, my sine of x is 1. At pi, my sine of x is 0. At 3 pi over 2, my sine of x is negative 1. At 2 pi, the sine of x is back to 0. And at 5 pi over 2, I'm back to a sine of x of 1. And so if I graph this, I get a function that looks something like this. Any output that is in the range of sine of x, so any output between negative 1 and 1, will give me actually infinitely many different values that I can use as inputs. So we are going to have to restrict our domain. So the easy way to see how we restrict our domain is I need to cover the entire range from negative 1 to 1, and I would like to be including 0 if possible. So the easiest way to do that is to go from negative pi over 2 to pi over 2. And so for sine of x, we restrict the domain to negative pi over 2 to pi over 2, inclusive to define the inverse sign. So one way to think about that is if you're looking at the unit circle, we are restricting our domain to, well, we get the y values on the unit circle, so we're going to be restricting our domain to following this half of the unit circle from negative pi over 2 to pi over 2. We can do the same kind of thing with cosine of x. For the cosine of x, if we graph that at negative pi, the cosine of x is negative 1. At negative pi over 2, we're looking at the x value, so the cosine of x of negative pi over 2 is 0. At 0, we have a cosine of 0 is 1. Cosine of pi over 2 is 0. The cosine of pi is negative 1. The cosine of 3 pi over 2 is 0. The cosine of 2 pi is 1. And the cosine of 5 pi over 2 is 0. And that gives me a function that looks like this. For this, if I were to restrict myself with the same restriction from negative pi over 2 to pi over 2, I would have one output that has two different inputs and nothing in the negative range. So we need a different restriction. We would like to still include 0, so instead of restricting from negative pi over 2 to pi over 2, we're going to restrict from 0 to pi. This covers the entire range, negative 1 to 1, and includes 0 and gives me just a single domain restriction. So, for cosine of x, we restrict the domain to 0 to pi to define the inverse cosine of x. Another way to think about this is on the unit circle, cosine represents the x values, so to get all of the x values I need to look at 1/2 of the circle in this direction. So from 0 to pi. Now, when we look at tangent, things get a little bit more interesting. So for the tangent function, tangent of x is equal to sine of x over cosine of x. And so anytime cosine of x is 0, we will get tangent of x is undefined. So we expect that whenever the cosine of x is 0, we will have a vertical asymptote for the tangent of x. And so we get that set of vertical asymptotes. Whenever sine of x and cosine of x are both negative or both positive, we get positive values. Whenever one is negative and the other is positive, we get negative values. So we end up getting a function that is looking like this. And if we are restricting our domain, we would like to include 0. And if possible, we would like to have a single continuous domain. So to make that happen, I can look at from negative pi over 2 to pi over 2. However, tangent isn't defined at pi over 2 or negative pi over 2, so we won't include the endpoints. So for the tangent of x, we restrict our domain to negative pi over 2 to pi over 2, not including the endpoints, to define the inverse tangent of x. So if we think about the unit circle, tangent of x is positive in the first quadrant, negative in the second, positive in the third, negative in the fourth. I need to include a single section of the circle that includes both a negative and positive. And so I could go from negative pi over 2 to pi over 2, or I could go from 0 to pi. However, if I go from 0 to pi, I have a hole in the middle of my domain at pi over 2. So we restrict our domain so that we are looking at negative pi over 2 to pi over 2. A similar type of argument applies for the cotangent of x. If we look at the cotangent of x, that's equal to the cosine of x over the sine of x. So this has a vertical asymptote everywhere where the sine of x is equal to 0. So that means we have a vertical asymptote here, 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 and here. And this is positive whenever both sine of x and cosine of x are positive or both are negative, and negative if one is positive and the other is negative. So we get a function that looks like this. Now, we can't include 0 this time because 0 isn't, the cotangent of 0 isn't defined. But we would still like to have that same basic area of the circle, and we would still like to have a continuous domain restriction if possible. So for cotangent of x, we restrict the domain to 0 to pi to define the inverse tangent, the inverse cotangent of x. Once again, if we're looking at a unit circle, cotangent is positive in the first quadrant, negative in the second, positive in the third, negative in the fourth. I could look from negative pi over 2 to pi over 2, but that gives me an undefined spot at 0. So instead, I'm looking at a restriction of the domain of 0 to pi. We are not including the ends because cotangent of x is not defined on either 0 or pi. For secant and cosecant, we have a little bit more complicated situation. So the secant of x is equal to 1 over the cosine of x. So everywhere where the cosine of x is 0, we expect a vertical asymptote. And when the cosine of x is 1 or negative 1, the value of the secant of x is going to be 1 or negative 1. And as the cosine of x gets closer to 0, you're dividing by a smaller and smaller number, which is making the secant larger and larger. So the secant of x function looks like this. And if we've got this as our secant of x, we would like to include 0. It's natural to say, oh, well, negative pi over 2 to pi over 2. However, if we look at negative pi over 2 to pi over 2, we're not getting the entire range, and there are places where we would get two inputs for a single output. So we have to restrict our domain from 0 to pi instead. And the problem with that is the secant isn't defined at pi over 2. So for secant of x, we restrict the domain to 0 to pi over 2, not including pi over 2, union pi over 2 to pi, to define the inverse secant of x. On the unit circle, we're looking at 1 over cosine to get, so we're looking at 1 over the x values, which means that we've got to be looking at the full range of x values, but this means that we have to exclude that pi over 2 because dividing by 0 isn't defined. Cosecant of x is the same idea. Cosecant of x is equal to 1 over sine of x. So when we graph this, we get these asymptotes, and the function is looking like this. And for our restriction, in order to cover the entire range, our restriction is going to be from negative pi over 2 to pi over 2. But we have to not include 0. So for cosecant of x, we restrict the domain to negative pi over 2 to 0, union 0 to pi over 2, to define the inverse cosecant of x. On the unit circle, we're looking at all the values for sine, so we're going to be using this half of the circle, but cosecant isn't defined at 0, so we have to exclude the 0 angle. And that shows how we restrict the domain so that we can define all of the inverse trigonometric functions.